Hello! In this video, I'm going to go through the midterm review questions, just highlighting my answers here. Number one, I feel like is very self-explanatory. Number of who chose a design with black, so I'm just adding up those three. For the men, it's 44, greater than the number who chose a design with blue. I'm adding up those three, it's 56, not true. And number two, I have to recognize this is a population distribution. We're just talking about one order. So the distribution is approximately normal. I'm going to calculate a z-score, the value minus the mean divided by the standard deviation, and then use normal CDF. Just a reminder, every time you use normal CDF, you should always be using the standardized values, meaning the z-score and 0 and 1 as your mean and standard deviation. Because this is multiple choice, you don't have to show any work, but I want you to know where it's coming from. Number three, continuous random variable. That means it can take on any single value. Items sold at a craft booth, that would be like 0 or 1 or 2. I can't sell like 0.6 items. Same thing for B, C. Anything on measurement is almost always going to be a continuous random variable, which this is. Number four, range is max minus min. So max, min, those are not the same. The medians are not the same. The minimums are not the same, and the maximums are not the same. IQR is quartile 3, which is this value, quartile 1, this value. Those are going to be the same. Number five, Roger claims that two stats likely to change greatly when an outlier is added are the mean and median. No. If you remember, the mean and the standard deviation and the range are not resistant to outliers. The median and the IQR are resistant. So the mean will change, but the median will not. It might not change at all, or it might change ever so slightly. All right, question 6. This is a short answer question. As you can see, there's going to be a lot of writing and reading that goes into it. So they give you these what are called parallel box plots. Write a few sentences to compare the distributions. So what you should be thinking about when you see compare the distributions is VSCO. You need to think about comparing variability, shape, center, and outliers. So here, there's more variation in the sugar content for the 1 cup, more variation. I can see that pretty obviously. The box plots differ in shape. The 1 cup distribution is skewed left. I know that because there's more variation in the lower 50% of the data. And the 3/4 cup is about roughly symmetric. The center, the median for the 1 cup is bigger or larger than the median for the 3/4 cup. And there's no outliers or unusual features like gaps, so I didn't even mention that. Part B, what new information do we have? So I'm really comparing this old box plot for 3/4, this old one to this new one. Well, when I look at the differences, this was shifted up because it was at 10, now it's centered at about 13.5 maybe. So it shifted up towards higher sugar contents per cup, and there's more variability. It was stretched out. So really talking about those two things, the increased center or the shift up and the increased variability as well. For part C, now they ask you to talk about the mean amounts. Well, keep in mind, these are the medians, so that's something to be careful of. The top distribution is skewed left, so the mean is going to be less than the median. The bottom distribution is roughly symmetric, so mean and median about the same. So if this mean is less and this is about the same, then I can conclude the mean for the 1 cup distribution is going to be less than the mean for the 3/4 cup distribution. So those questions cover chapter 1 and 2. All right, looking at number 7. This is pretty self-explanatory. The number of on-flight times at airport S, well, that looks like 100 is half of that at T. T is 200. They're not even talking about percentages, it's just numbers, so that's what I think makes it a little bit easier. All right, correlation is 0.994. Why does that mean the linear model might not be appropriate? or A doesn't make sense. You can have a correlation other than those two where you have a linear model that's appropriate. A correlation of 0 means really you have no linear association. We don't need cause and effect. I believe they're just squaring the 0.94 to get this, your coefficient of determination. Your correlation, remember, it measures the strength and direction of the model. We don't know if it's a linear model or not. It could be curved, so that's why the answer is E. Okay, and question 9 has no logical interpretation. This would be the y-intercept. That would be somebody with a collar size from the height. Somebody who's 0 inches tall has a collar size of -94. Makes no sense at all. Question 10. This is definitely not linear. You can see a curved pattern here. And I'm just looking for the choice that displays that best. As the percent of woodland increases, the number of deer decreased quickly, and then it flattened out. That's really what's happening. Number 11, this is a re-expression, I can tell because of the logarithm. So I'm just substituting in 4.8. I get to this point, and then I can do second log on my calculator, and it'll automatically give me 10 raised to the power. Or if I know log means exponent, the exponent is 0.1, the base is 10. I can rewrite this and then substitute that in to get the 1.26. Or if you didn't know any of that, plug this in, you get 0.1, and just type in your calculator log of 0.1, log of 0.68, etc., and figure out which one of these equals 0.1. Question 12. Here's your linear regression. You're interpreting the slope. Remember, this column here that says coefficient, I know it's a pain in the butt because it's split onto 2 pages. Your coefficient column is where you're looking for your slope and y-intercept. Constant, that's your y-intercept. Winds, that's your explanatory variable. The number in front of that's your slope. So the slope's 235. You'll notice I wrote the equation. I think that's helpful. And as x goes up by 1, the predicted y increases by, in this case, 235. Part B, why is it not reasonable for your y-intercept? Well, you're going to play 0 games, or you have 0 wins. There's not going to be anyone there if you're not playing any games. And we only have data between 64 and 104 wins, so there's extrapolation happening here. We don't have any data about the attendance for a team with 0 wins. So I guess they could play games and just not win. So I guess the bigger issue is here is the extrapolation. Correlation coefficient. That's a fancy way of saying what is R equal. So here I take R squared, and I'm just going to convert it to a decimal, and then I'm going to take the square root of that. And I could get plus or minus. So I need to look specifically at this case at the slope. The slope's positive, or I can look at the scatter plot. It has a positive direction. Those tell me that it's going to be the positive correlation, in this case of 0.35. Part D, what's going to happen if we remove this point? So if I take this point out, this point is kind of has some high leverage. Wherever x bar is, maybe around like 82, 83, that's kind of far away in the x direction. So it's going to pull the line towards it. So if I get rid of this point, that line's going to drop down, which means the slope just increased. It went from being relatively flat to steeper. The other thing is asked about the correlation. If I get rid of this point, now I have less scatter in the scatter plot, which means I have a higher correlation, stronger linear form. Okay, question 13. What can we not conclude? This is one of the most important things that we'll talk about the whole year. Association doesn't prove causation. This is not an experiment. They're just observing. So this is D. 14, completely randomized design is when you just randomly assign the treatments to the subjects and you don't have a blocking variable. So the plans are being randomly assigned to the workers. One of those 3 plans. That's it. Question 15. I had to read this a couple times. There's a lot going on here. Remember, a confounding variable is something other than your experimental variable, or I'm sorry, your explanatory variable or your factors that you're testing. In this case, we're testing the dose and the cell type. So we want to be able to say the dose or the cell type caused the change and nothing else. Well, the problem is here, they are going to have consistency from one replicate to the next. The researcher decided to use 4 lab technicians. One technician would be assigned the high dose with strain A. So they would be doing all of those. So the problem is, if there's something that in the way that they're doing it, that might be causing the change, and it's not the different dose or the cell type. So that could potentially confound our experiment. All right, that's the first half. I'm going to stop here and I'll make a video for the second half.